Now let's talk about what happens when you add a strong base to a buffer. So we're going to consider the same buffer solution that we saw in our last video. We have a solution that has a concentration of HF of 1 molar and a concentration of NaF that's 0.5 molar. We found the pH of that solution to be 2.84. Let's say that we're using 40 milliliters of this buffer solution. And now to this buffer solution, we're going to add 2 milliliters of 1 molar sodium hydroxide. We're adding a strong base to the buffer, and we need to figure out what the new pH of the solution will be after adding the NaOH. Let's talk through how we're going to solve this problem. This problem is fairly involved. There are a lot of steps to solving it, but fortunately, there's a very systematic way of solving this problem that's going to be similar to problems that you've seen in the past. So I recommend taking really good notes, following along through this, and then trying this problem again on your own so that you can see what all the steps are in solving it. The first step is to write the list of major species that you have in your solution before any acid-base reactions occur. That's crucial. It's where you always want to begin any problems where you're dealing with acid-base chemistry and you want to know the pH. So our buffer solution contained HF and NaF. Remember that HF is a weak acid, so we want to keep it together as HF. NaF is a soluble salt, and so it dissociates into Na plus and F minus. We've also added sodium hydroxide to this solution, and so sodium hydroxide is a strong base. We should dissociate any strong bases. Remember, the rule on that is dissociate soluble salts, strong acids, and strong bases. All of those S sort of sounds. So we will break up the NaOH to give us more Na plus and OH minus, and water is always a major species in any aqueous solution. Writing the list of major species helps you to determine where you go next. It helps you to determine what chemical reaction will occur and what type of a problem you're dealing with. The rule on writing the reaction is that the strongest acid in your solution will react with the strongest base that you have in your solution. So we have to go through the list of major species that we have here and think about whether they're acids or bases or spectators and how strong or how weak they are. HF is a weak acid. Na plus is just a spectator. F minus is a weak base. Hydroxide is a strong base. And water is a very weak acid or a very weak base. It's the weakest acid and it's the weakest base that we deal with. All right, so we know what the strongest base is here. That's the hydroxide ion. That's going to react with the strongest acid that we have in our solution. We have two choices. We can choose HF or we can choose water. Those are the only two acids that we have. Neither of them is strong, but we have to pick which of the two is the strongest. And HF, as a weak acid, is stronger than H2O, which is a very weak acid. So the strongest acid that I have in my solution is HF. The strongest base that I have in my solution is the hydroxide ion. These two will react with one another. Now, since OH minus is not just the strongest base, but it's also a strong base, it's going to react to completion with the HF. And when you see to completion, that means that we are dealing with a stoichiometry problem. I'll remind you, back in chapter 7, one of the things that I had mentioned was, if you see a strong acid or a strong base, you want to be thinking stoichiometry. All those S sounds go together. When we have a stoichiometry problem, we're going to write the reaction using a one-way arrow. The reaction goes all the way to completion. HF reacts with the hydroxide ion. To completion, use a one-way arrow. And let's see, so the hydroxide ion is a base. It's going to gain a proton to become H2O. F minus is an acid, so it loses a proton to become the fluoride ion. Now, we have to do the stoichiometry. We're given the amounts of HF, hydroxide, and F minus that are present. And since we're given the amounts of both of our reactants, HF and hydroxide ion, we're dealing with not just a stoichiometry problem, but a limiting reactant stoichiometry problem. We learned how to do limiting reactant stoichiometry problems back in Chem 1A. Let's talk through that process. So in Chem 1A, we did stoichiometry limiting reactant problems by writing out a bunch of conversion factors and lines where we did all these mole ratios. But there is a really quick and organized method that you can use for doing stoichiometry problems when you have a chemical reaction that involves a 1-to-1 mole ratio. And this method is called using a before and after table. It's similar to an ICE table. The only difference is you would do a before and after table for when you have a stoichiometry problem, when you have a reaction that goes to completion. You make an ICE table if the reaction goes to equilibrium, and if you have the two-way arrow in the reaction. It's just a very organized way of doing the stoichiometry that can be a time saver when you have a 1-to-1 mole ratio in the problem. One more thing that's worth mentioning is when you do stoichiometry, you must always use moles. And so when you make one of these before and after tables, the units that get plugged into it are moles. This is distinct from an ICE table, which uses either concentration or pressure. In a before and after table, you're doing stoichiometry, and so you must use moles. The problem has given us molarities and volumes, and so to find the moles, we have to multiply molarity and volume. I'll remind you, we saw this back in Chem 1A last quarter. Molarity is equal to the number of moles divided by the volume, moles per liter. And so if you want to find the moles, you have to multiply volume times molarity. With that in mind, let's now go about making the before and after table so that we can do the limiting reactant stoichiometry part of this problem. We'll write the reaction out, and then we'll have a line for what's present before. We'll have a line for what goes on during the reaction, and a line for what's left over after the reaction. Now we'll start filling it out. We have to find the moles, again, by multiplying the molarity and the volume. The HF comes from the buffer solution. We were told that the volume of the buffer solution was 40 milliliters, and so you want to use 40 milliliters or 0.04 liters as the volume for the HF solution. Furthermore, you were told that the concentration of HF in the solution was 1 molar, and so you would multiply that by the concentration of HF, 1 molar or 1 mole per liter. So before the reaction occurs, you have 0.04 moles of HF. The F minus also comes from the buffer solution, and so you want to use the volume of the buffer solution, 0.04 liters, and the concentration of the fluoride ion, right, from the NaF was 0.5 molar. So the concentration of the fluoride ion is 0.5 molar, 0.5 moles per liter. So you have 0.02 moles of the fluoride ion before the reaction occurs. The hydroxide ion comes from the NaOH. So we have to look at the volume and the molarity of the NaOH solution to find out how many moles of hydroxide there are. You were told that you use 2 milliliters of the NaOH solution. So the volume there is 2 milliliters or 0.002 liters. And the concentration of the NaOH solution was 1 molar, so 1 mole per liter for that. 0.002 moles of the hydroxide ion. And just for the sake of completeness, when you look back on this problem and you want to see where all the numbers came from and you know how we knew all of this, right? The HF was from the buffer. The F minus was from NaF in the buffer, right? And so that's why you use the volume of the buffer for the HF and for the F minus. And the OH minus was from the 2 milliliters of NaOH added. Just to keep it all straight so that you know where all those numbers came from here. For the water, who cares? Not part of the K expression, not part of the Q expression, not going to have any effect on concentration of H plus at equilibrium or the pH. Now, because this is a stoichiometry problem, the reaction will go all the way to completion until you use up all of the limiting reactant. We need to figure out which of the two reactants, HF or hydroxide, is the limiting reactant. And when we compare the numbers of moles and recognize that this reaction occurs at a 1-to-1 stoichiometry, if it occurs at a 1-to-1 stoichiometry, whatever we have fewer moles of will get used up first. Since we have fewer moles of hydroxide, the hydroxide is the limiting reactant. The hydroxide will get completely used up. Importantly, whenever you do one of these before, during, and after tables, whenever you're doing stoichiometry, one of your reactants must always go to 0. You will always consume all of whatever your limiting reactant is. In this case, it's the hydroxide ion, so all of the hydroxide gets consumed. There will be none of it left after the reaction goes to completion. Knowing that allows you to fill out the rest of the table, because if you start with 0.002 moles of hydroxide and you finish with nothing, that means you must have reacted 0.002 moles of hydroxide. Due to the 1-to-1 stoichiometry of this reaction, you must have also reacted 0.002 moles of HF. And again, due to the 1-to-1 stoichiometry, you must have produced 0.002 moles of fluoride ion. Now, you can combine everything to find how much is left over for the HF after the reaction. 0.04 minus 0.002 is 0.038 moles of HF. And for the fluoride, you start with 0.02 moles, and then you make another 0.002 moles. So after the reaction, you'll have 0.022 moles of F minus. So one more point worth making on this, just to remember here, is when you do stoichiometry, all of the limiting reactant gets used up. Something on the reactant side of the table has to go to 0. And that knowledge helps you to be able to figure out what's going on with the rest of the table. All right, so I happen to like doing the stoichiometry in this way. I think that this is a little bit quicker and a little easier maybe than doing the stoichiometry where you have to write out all the mole ratios and do all the conversions and all of that. However, it's really best to only do this when you have a reaction that occurs at a 1-to-1 mole ratio. If you have a mole ratio that's different from that, these tables can be a little bit more tricky to fill out. Now, every single time that you complete one of these before, during, and after tables, you have to reevaluate the list of major species that are present in your solution. Because when you do stoichiometry, you completely use up your limiting reactant, meaning that it is gone. It is no longer part of the list of major species. The list of major species will always change after you do a before, during, and after table. So after you're finished with it, you have to reevaluate what's present in your solution. We can start by looking at what we initially had as a major species, right? We had HF, Na+, F-, hydroxide, and water. So we can ask ourselves, do we still have HF? Yes, we still have 0.038 moles of that. So that goes on the list. All right. Na+, that was just a spectator, so none of that got used up. That's still there. What else? F- was initially present. And we see that now there's even more of it than what we initially had. So that's still on the list. The list initially also included the hydroxide ion. And from the table that we made here, what we saw was that all of the hydroxide got used up. Right? The hydroxide went to 0, so that's no longer on the list of major species. And then lastly, we have water, because we always have water in an aqueous solution. That's the new list of major species. All that we've done is wiped out the hydroxide because the hydroxide has been completely used up. Now, after writing the list of major species, we use that to help us determine where to go next in the problem. We're going to figure out what type of a problem we're dealing with now and what strategy we use to solve it. Because we no longer see H+ or hydroxide, we don't have to worry about that reacting anymore. So now all we have to do is ask ourselves, do we have a buffer solution, right? Because if we identify that we have that type of a problem, then we'll have some strategy on how to solve it. Because we see that we have both a weak acid, HF, and its conjugate base, F minus, the answer to this question is yes. We do have a buffer. So we have both a weak acid, which you could generalize as HA, and its conjugate base, A minus, as major species. So since we have a buffer, the strategy that we can use to find the pH is simply using the Henderson-Hasselbalch equation. You could, if you really wanted to, make an ice table, but why? Let's just use the Henderson-Hasselbalch equation to find the pH when you have a buffer. Now, one point that's worth making regarding the Henderson-Hasselbalch equation is this. The Henderson-Hasselbalch equation says that pH is equal to the pKa plus the log of the concentration of A minus, in this case that's the fluoride ion, over the HA, in this case that's HF. Now, what we have after doing the before, during, and after table is moles. We don't have concentrations. But because of the way that the units cancel out in this problem, and because everything is all in the same solution, you can use moles and molarity interchangeably. Let's take a look at that and why it works in this type of a problem. So the pH is equal to the pKa plus the log of the concentration of F minus would be the moles of F minus over the volume of the solution. And that's divided by the concentration of HF, which is the moles of HF, over the volume of the solution. Because everything is all in the same solution, right? This is all in the same buffer. It's already been all mixed together. The volume is the same. And so that volume cancels out, leaving you with just the moles of F minus over the moles of HF. So you can save yourself the step of converting the moles back into a concentration at the end of the problem. You can simply just plug in the moles. This works when the buffer has already been mixed together and everything is all in the same solution, like it is here. All right, so with that in mind, the pH of this solution is equal to the pKa of HF, which is a given piece of information. It is 3.14 plus the log of, we found the moles of F minus were 0.022 moles over the moles of HF after the reaction goes to completion is 0.038. Again, it's all in the same solution. The moles cancel out, so you're good in terms of the units. Everything is fine. When you plug this into your calculator, you'll find that the pH of this solution after adding the 2 milliliters of 1 molar NaOH will now be 2.90. It started at 2.84, and now it went up to 2.90 after adding the sodium hydroxide. It makes sense that the pH should be higher after adding the sodium hydroxide. So it's good to think about whether that's a reasonable answer or not. If you got a number lower than the initial pH of 2.84, that would tell you that you made a mistake somewhere. All right, so that brings us to the end of this example. In the next example, we'll take a look at what happens when you add a strong acid to a buffer solution.